Do you know that you can create CUDA code automatically and easily using a visual language? My name is Rodrigo Rivera. Welcome to the presentation of GLG, Visual Language for Development of Parallel Programs in CUDA. Throughout this presentation, I will explain how it is possible to facilitate programming in CUDA. I will give you an introduction to parallel computing, its challenges and alternatives to facilitate development with visual languages, and then I will present my proposal. I will explain how the GLG development environment is built, the icon properties, and how the translation to CUDA code is done. Then I will show a qualitative comparison with textual programming and other visual languages. In the experiments and results sections, I will show two test cases to evaluate the performance of GLG against textual programming, to finish with the conclusions of the investigation and future work. There is a wide variety of problems that require parallel programs. Among them, we have atmospheric circulation, galaxy evolution, X-rays, and molecular simulations. These problems are solved using architectures with multiple processors and cores. In this work, we focus on NVIDIA graphics cards, since they can have thousands of cores working in parallel. However, what is the problem when we develop on graphic cards? This programming can be complicated because the programmer must know the architecture to fully exploit its performance. The programmer must know the different types of memories, warp size, maximum number of threads, in addition to synchronizing the threads correctly, since stopping a large number of threads can be very costly in runtime. For this, visual languages are useful for the creation of parallel programs, which hide both theoretical and implementation aspects, so it is a good way to attack this problem. Thus, we propose graphic language for GPUs and its development environment to facilitate the creation of CUDA programs by dragging icons, filling their properties, and facilitating communication between the GPU and CPU. First of all, I will explain the icons. The icons in GLG are classified into header icon, constant icon, communication variables icon, and CPU and GPU processing icons. Each icon has a set of properties that can be accessed and modified by clicking on it. The first one is the header icon, which allows selecting libraries containing subroutines to perform input and output operations, mathematical calculations, date and time formatting, among others. The constant icon allows setting fixed values that will be used in different parts of the program and will not change throughout its execution. The programmer must assign an identifier and a value to each constant. The communication variables icon allows exchanging data in the form of arrays between the CPU and GPU. The name in the CPU is assigned by the programmer, while the variable in the GPU is created by default. The programmer has the ability to select the variable type through a drop-down list, which allows them to choose from different data types such as integers, floats, or characters. Additionally, they must specify the numbers of elements that the array will contain. The input CPU icon allows to specify the code that is executed before calling a kernel. It is used to initialize or load the data to be processed on the GPU. The icon includes a section that allows selecting the communication variables to be sent to the GPU. The GPU icon allows selecting the number of threads to create on the GPU. It is also where the code is written to be executed on the graphic card, in such a way that the processing work is divided among the threads. The output CPU icon allows to specify the code that is executed after the kernel has finished its execution. Additionally, this icon is used to receive the variables selected by the programmer. which come from the GPU device. The output icon stores the response from the API REST when executing the program build on the remote CUDA environment. With the explanation of these icons complete, I will proceed with description of the GLG language. The GLG language is based on a grammar consisting of 3 production rules. The first rule, called program, can be derived in rule 2 or rule 3. This means that the non-terminal symbol operations can be replaced by rule 2 or 3. Furthermore, rule 2 can derive into itself or rule 3. The architecture of the development environment consists of 3 elements. The first one is the remote CUDA environment, the second is the API REST, and finally the web interface. The remote CUDA environment is a server that has an installed NVIDIA graphic cards and its drivers. The configuration allows for compiling and running CUDA programs. The access to the remote CUDA environment is through an API REST, which enables the transmission of information using HTTP protocol over the internet. The main services offered by the API REST are compiling and executing CUDA code and returning the output. Another service is obtaining information and characteristics of the graphic card. The GLG web interface features an intuitive structure that facilitates the creation of programs in the language. The top menu, labeled with number 1, provides options to start building CUDA code and obtain detailed information about the graphic card's features, enabling the programmer to better understand the available processing capabilities. The menu labeled with number 2 allows adding more processing icons. The workspace area marked with number 3 is the main space where GLG programs are developed, and the section marked with number 4 displays the code constructed from the icons. Once the program in GLG has been constructed using the web interface, the code and logic of the visual language are stored in a list of objects that represents each of the icons and the connection between them. During the translation process, each object in the list is parsed and the corresponding CUDA code is generated based on the properties and settings of each icon. Next, I will explain how the translation of GLG components to CUDA is performed. In the translation of the header, the name of each library selected by the programmer is inserted into the corresponding syntax of the include statement. This ensures that the required libraries are available and correctly included in the final program. In constant translation, the identifier and value of each constant are inserted into the defined syntax. In this way, the constants defined by the programmer will be available throughout the program. From the communication variables, the translation is performed to create a variable on the CPU and allocate memory using the appropriate C syntax. This is achieved by using the memory allocation instruction malloc. Similarly, for the GPU, CUDA syntax is used to create a variable and allocate memory on the GPU using the CUDA malloc instruction. The translation for the exchange of information between the CPU and GPU is obtained from the properties of the communication variables. The main copy instruction is used to specify the source and destination of the data to be transferred. The kernel function definition is built from the information in the communication variables. Input parameters are included as well as their data types. The GPU icon contains the textual code that the programmer inputs. In addition, GLG is also responsible for generating the kernel invocation instruction inside the main method. Using the information from the communication variables and the information from the graphic cards, the appropriate syntax is generated to assign the number of blocks threads and arguments when calling the kernel function. Each of the translations performed in GLG is stored in an object list, which facilitates access to the individual fields of each translation and allows maintaining a logical order in the generated code. This object list structure ensures that translations are consistently organized and can be accessed in an orderly fashion during final code generation. Additionally, the object list also stores the relationship that exists between neighboring icons in the GLG interface. This information is crucial for determining the order in which the translated code should be assembled. To perform a qualitative comparison, 4 criteria were used to evaluate GLG characteristics. The first of these criteria is expressiveness. Expressiveness refers to ability of language to express through icons, sequential tasks, branching, loop structures, input and output operations, and data communication. Applicability refers to the range of programs that can be created using the language. This evaluation is determined by the grammar of the language, which establishes the rules and restrictions for the construction of programs. Interaction level refers to how the programmer builds programs using drag and drop, grouping, reordering, workflow zooming, and cloud access. Portability refers to ability of the language to be used on different platforms and execution environments. A portable language can run on different operating systems and hardware architectures without requiring significant modifications. Now, I'm going to present 2 qualitative evaluations. The first evaluation is shown in this table, where a comparison between CUDA and GLG is present. The first column presents the features explained above, and subsequent columns assign a score from 1 to 5 for each feature, with a lower score indicating a deficiency in that feature. As observed, GLG may have limitations in terms of applicability, since some more complex or specialized tasks may require a higher level of detail and precision that can only be achieved with textual languages. However, GLG automatically generates code and makes it easy to write complex instructions, such as creating and sending variables between the CPU and GPU. In addition, GLG allows the programmer to modify the generated code before executing it, in case they have more detailed knowledge of CUDA to optimize or improve the instructions. The second evaluation is shown in this table, where a comparison is made between GLG and visual languages reviewed in the literature. It can be observed that GLG has a good expressiveness by providing a visual environment for the development of programs, which includes a considerable number of icons that represents operations clearly and consensually, unlike CUDA block and GPU block, which have a large number of icons that increase the learning curve of the visual language. In terms of applicability, GLG can be focused to solve problems in different programming areas, such as scientific computing, simulation of complex systems, and parallel data processing. On the other hand, the GLG environment offers a high level of interaction by providing an interface where programmers can drag and drop icons, modify their properties, and establish connection between them, unlike OpenCLGen, which hasn't draggable elements. Finally, GLG environment improves portability compared to CUDA block and GPU block, as it can run on different platforms with a web browser and internet connection. Regarding performance evaluation, a comparison was performed using 2 test cases. The first test case corresponds to Voronoi diagrams. These diagrams are used to divide a space into adjacent regions, where each region is associated with a specific point called a generator. This figure shows the graphical representation of a Voronoi diagram. Voronoi diagrams have various applications in areas such as robotics, where they are used to plan the path of a robot. It is also applied in 3D modeling for the generation of objects created with polygons. A parallel solution for the generation of Voronoi diagrams is based on a two-dimensional matrix with n rows and m columns, where a set of rows is associated with each thread to distribute the workload. The region is obtained by calculating the Euclidean distance of the element in question against all the generators, and the smallest distance obtained is recorded. Finally, the region to which the element belongs is determined according to the generator associated with that shortest distance. The second test case is the calculation of the area under the curve. In this problem, the Riemann-Sum technique is used to approximate the area under the curve of a function in an interval. Riemann sums are a mathematical tool that allows estimating areas using a very small partition of the interval and taking the value of the function of each subinterval as an approximation of the height of the rectangle. For this, the area of each rectangle in the interval is calculated and all the areas are summed to obtain an approximation of the total area under the curve. The greater the number of rectangles, the better approximation. An efficient and fast strategy for parallel point evaluation is to partition the interval among the number of threads to calculate the sum of the partial areas. Once each thread has completed the calculation of its partial area, the total sums of all partial areas is computed on the CPU. For performance evaluation, we perform 50 executions of Voronoi program to obtain a trend. We varied the number of threads and record the execution times for both the GLG generated program and the textual version. The graph clearly shows that the execution times for both versions are equal, indicating that the efficiency of the code generated by GLG is on par with the traditional implementation in terms of performance. This result is significant as it demonstrates that GLG can produce code with comparable performance to manually written CUDA code, validating the effectiveness of the Vision language in achieving high performance parallel computing tasks. Similarly, for the test case of the area under the curve, we also perform 50 executions, varying the number of threads, and record the execution times for the code generated by GLG and its textual version. The graph shows that the execution times for both versions are also very similar. These results suggest that GLG is able to generate code with similar efficiency to textual programming in CUDA. This is important as it demonstrates that the visual language doesn't introduce significant overhead in terms of performance and allows developers to take advantage of graphic cards programming without compromising the efficiency of the result code. In this work, an innovative visual language for programming on NVIDIA graphic cards was proposed. A grammar has been defined that allows building programs in a logically structured way, which improves the applicability of the language in various scenarios. To facilitate programming in GLG, a web environment was developed that provides support for executing CUDA codes through an API REST. Web architecture contributes to the portability of the GLG environment, allowing it to execute on different platforms and devices. The automatic code generation and the ability to make manual modifications provide flexibility and adaptability to the language, striking a balance between the simplicity of visual programming and the complexity of textual programming. GLG offers several advantages over traditional textual languages, such as the use of icons and workflows to facilitate the understanding and visualization of programs. As a future work, the following lines of research and improvement are proposed. Identification of new icons. Adding icons that can further facilitate programming on graphic cards. Support for n-dimensional data. Being able to handle n-dimensional data in communication variables. This will enable programmers to work with more complex datasets. Saving and loading of GLG-specific files. Work on the implementation of functionalities that allow saving and loading files in GLG's own format. Finally, the creation of methods and functions for GPU and CPU. This will allow greater flexibility in designing programs. Thank you for your attention.